You stand up from a chair a little too fast, and for one strange half-second, your legs hesitate. Like the message arrived before the muscle did. You catch the edge of the table. Your heart does that small, private lurch, and for a second you're almost embarrassed, glad nobody happened to be standing there to see it. Then it passes, and you go on with your day, and you probably never think about it again. I want to tell you exactly what happened in that half second, because it isn't weakness in the way you've been told to think about weakness. And I want to tell you about a strange wrinkle in the research on a very ordinary supplement, one usually marketed to 22-year-olds trying to get bigger biceps in a college gym. That, according to a study where researchers watched this exact process happen live, inside real human muscle, using an MRI machine, works roughly twice as well once a person is past their late 50s as it does in their 20s. Not a little better, about double. This isn't a video about hacking your metabolism or discovering some miracle powder. It's about one molecule, one very specific kind of muscle fiber, and a genuinely counterintuitive fact about aging biology that almost no fitness content explains correctly. By the end of this, you'll know exactly why creatine, yes, that creatine, can matter more to a 65-year-old's independence than it ever mattered to a 22-year-old's biceps, and precisely which part of your body is responsible for that half-second hesitation at the edge of the table. Let's start with what you can actually feel, because the feeling comes before the science, and it's more precise than people usually give it credit for. Notice that the wobble isn't the same thing as being tired. You can be perfectly rested, well slept, not remotely out of breath, and still get that hitch when you stand up fast, step off a curb that's an inch lower than you expected, or reach out to catch a dish sliding off the counter. That matters, because it tells you this has nothing to do with endurance. You're not gassed. Your heart isn't racing. What failed, for that fraction of a second, was speed. The ability to produce a large amount of force immediately, with no warm-up, no ramp-up, on the very first instant of demand. That's a completely different job than the one most people picture when they think about muscle. Carrying groceries up 3 flights of stairs, gardening for an hour, holding a plank. Those are endurance tasks, and they tend to hold up reasonably well into your 60s and 70s with normal activity. What quietly erodes first is the opposite skill, the sudden, explosive, all-or-nothing burst, the catch, the lunge for the railing, the push to get up out of a low chair without using your hands. Here's the part almost nobody explains correctly. Your muscles didn't get weaker in one uniform way, like a battery slowly draining across the board. They lost one very specific capability first, while keeping most of the others largely intact. This is also why grip strength, of all things, turns out to be such a reliable marker doctors and researchers use when studying health in older age. Not because gripping things matters so much day to day, but because it's a fast, simple way to measure exactly this kind of instant, explosive force production, the same capacity that's quietly failing elsewhere in the body at the same time. So which part of the muscle is responsible for that specific capability? And why does it go first? Skeletal muscle isn't one uniform tissue. Zoom into any muscle you own, say, the big muscle across the front of your thigh, and you'll find 2 fundamentally different types of fiber woven together, built for 2 fundamentally different jobs. One type is built like a marathon runner, slow to fatigue, rich in the machinery for burning oxygen, happy to fire gently for an hour at a stretch. Physiologists call these type I fibers. The other type is built like a sprinter, capable of producing enormous force almost instantly, but only for a few seconds before it's spent. These are type A fibers, and your body reaches for them for exactly the kind of effort that saved you at the edge of that table. Here's the finding that should surprise you, because it's the whole reason this video exists. When researchers actually study aging human muscle directly, the marathoner fibers barely change. It's the sprinter fibers that shrink and disappear, disproportionately, years before overall muscle mass looks obviously reduced. This isn't a guess. It comes from decades of work by researchers, including Jan Lexel, who examined cross-sections of thigh muscle from men ranging from their teens to their 80s, and found that the aging process is remarkably selective. Total fiber count drops with age, and the loss lands hardest and earliest on the fast, explosive fibers, while the slow, endurance fibers are largely spared. Lexell's data also placed a rough starting line on all of this. The decline traces back to around age 25, quietly, long before anyone would call themselves older, and then gradually picks up speed from there. There's a reason those particular fibers go first, and it traces back not to the muscle itself, but to the nerve wired into it. Every muscle fiber takes its orders from a single motor neuron, and it's that neuron's own firing pattern that tells the fiber whether to behave like a sprinter or a marathoner. Motor neurons are themselves cells that can be lost with age, and the ones controlling fast, explosive fibers appear to be disproportionately represented among the losses. When a fiber's original neuron goes, a neighboring neuron can sometimes reach over and adopt it. But if that neighbor happens to be one of the slower, marathoner type, the adopted fiber gradually starts behaving more like a marathoner too. So the sprinter fiber doesn't only disappear from a shrinking head count. In some documented cases, it gets quietly converted into something else, which explains something that used to genuinely puzzle me: why an older person can often still walk for miles, garden all afternoon, stand at the stove cooking dinner for an hour, and yet lose their footing in a way a younger version of themselves never would have. It was never a general decline. It was the sprinter leaving the team while the marathoner stayed on. So now we know where to look. But knowing which fiber is vanishing doesn't yet tell us why creatine, of all things, would matter here. For that, we need to go one level smaller, down into the actual chemistry of how a muscle fiber produces force in that first fraction of a second. Every contraction in your body, from blinking to sprinting, runs on the same fuel, a molecule called ATP. Muscle doesn't burn fat or sugar directly for instant power. It burns ATP, and it only keeps a tiny reserve of it on hand at any given moment, enough for a second or two of real effort. So the question becomes, what refills ATP fast enough to keep a sprinter fiber firing? There are a few different refueling systems in the body, and they run on wildly different timescales. Burning fat is efficient but slow. Good for a long walk, useless for catching yourself off a curb. Burning sugar without oxygen is faster, but it still takes several seconds to ramp up to full speed, and it leaves behind a byproduct responsible for that familiar burning feeling in the muscle. Neither system is fast enough to cover the very first instant of an explosive, unplanned movement. It's worth pausing on why your body bothers keeping several separate systems on hand instead of one really good one. The honest answer is that no single system is good at everything a body needs. Fast systems run out almost immediately. Efficient systems take too long to spin up. So the design isn't one winner. It's a relay, each system covering for the next one's weakness, handing off from the fastest and shortest lived to the slowest and most enduring as an effort stretches from an instant into a minute into an hour. For that first instant, your body keeps something else on standby, a molecule called phosphocreatine, sitting right there inside the muscle fiber, ready to hand off its phosphate group and instantly regenerate ATP the moment it's needed. The actual handoff is carried out by an enzyme called creatine kinase, which does nothing else but sit there, waiting, ready to snap that phosphate group off phosphocreatine and onto a spent ATP fragment the instant a contraction demands it. Phosphocreatine has neither of the other system's problems. It's already preloaded, needs no ramp-up time, and leaves behind no burning byproduct. Think of it as a quick-charge battery pack sitting next to the main power line, not meant to run the show for long, just meant to deliver an instant, explosive burst the second the demand hits, faster than any other system in the body can respond. And here's the detail that connects everything back to those sprinter fibers. Type I fibers are packed with far more of this quick-charge battery than Type I fibers are. It makes sense once you see it. A fiber built for a 100-meter dash needs a battery built for a 100-meter dash, not one built to trickle charge for an hour. The exact fibers built for instant, explosive output are the exact same fibers stocked with the most phosphocreatine, which means we now have two facts sitting side by side that, on their own, seem unrelated, but together explain that half second at the table. Fact 1. Aging preferentially kills off Type I fibers. Fact 2. Type I fibers hold most of your body's quick-charge battery capacity. Put those together, and a muscle that's aged hasn't just gotten a little smaller. It's lost a disproportionate share of its instant power reserves specifically. Go back to that half second at the table for a moment, now that you have the actual mechanism in hand. In that instant, your nervous system fired off a command for sudden, forceful correction, and it was your thigh's type E fibers running on their onboard phosphocreatine that were supposed to answer it instantly. If there are fewer of those fibers left, and the ones remaining are carrying a smaller charge, the response you get back really is measurably smaller and measurably slower than it used to be. Not because you lost your balance in some mysterious way, because the specific hardware built for exactly that job has quietly shrunk. But it goes one step further than that, and this is where the story gets genuinely interesting. It's not just that you have fewer of these battery-rich fibers as you age, the battery itself. The actual concentration of phosphocreatine sitting inside the muscle fibers you still have tends to run lower to begin with. Research groups have measured this directly, using a scanning technique called phosphorus magnetic resonance spectroscopy, and it's worth pausing on how clever that technique actually is. Phosphorus atoms behave very slightly differently inside a strong magnetic field, depending on exactly which molecule they're attached to, and both ATP and phosphocreatine happen to contain phosphorus. So instead of ever cutting into anyone's leg, researchers can put a volunteer's thigh inside a scanner, have them exercise right there on the table, and watch the phosphorus signal shift back and forth between the two molecules in real time, painlessly, over and over, in the same living person. Using exactly that method, most, though not quite all, of these studies have found resting phosphocreatine levels to be lower in older adults than in younger ones, with the picture varying somewhat depending on which specific muscle gets measured. Part of that lower starting point comes from something simpler than muscle biology. Creatine is only made by your own body in modest amounts, synthesized quietly in the liver, kidneys, and pancreas, and the rest normally comes from diet, almost entirely from meat and fish. Appetite, food variety, and overall intake often drift downward with age for reasons that have nothing to do with muscle science specifically, and a smaller dietary contribution compounds directly onto a fiber population that was already storing less to begin with. And it's not only that the tank tends to start more empty, the refill process itself slows down. After a hard contraction burns through phosphocreatine, your body has to resynthesize it, recharge the battery, before the next burst is available. That recharging is powered by the mitochondria, the oxygen-burning engines inside the cell, and multiple studies using that same real-time scanning technique have found this specific recharging process measurably slower in older muscle than in younger muscle. Here's the part most people get wrong when they hear, "your mitochondria decline with age." They picture something vague and irreversible, like rust settling in. It isn't that. It's a specific, measurable, mechanical slowdown in one particular recharging process, in one particular kind of fiber. And mechanical problems, unlike rust, sometimes have surprisingly direct fixes. Which brings us to the part of this story that made me want to make this video in the first place. In 1998, a research team led by Sinclair Smith at Boston University ran an experiment that, as far as I'm concerned, should be far more famous than it is. They took two groups of ordinary volunteers. One group in their late 20s and early 30s, another averaging 58 years old, and had them perform repeated leg exercises while lying inside a whole-body MRI scanner so researchers could watch phosphocreatine levels rise and fall inside their thigh muscle in real time without ever cutting the skin. First, they measured everyone's natural baseline. Exactly as the earlier research would predict, the older group started with noticeably lower resting phosphocreatine, and their recharge rate after exercise was measurably slower than the younger groups. Then everyone took creatine for 5 days, a completely ordinary amount, nothing exotic, and went back into the scanner. In the young group, resting phosphocreatine rose by about 15%, a real, respectable improvement. But in the group averaging 58, under the exact same protocol, it rose by roughly 30%. Almost exactly double the relative gain of the younger group, and their sluggish recharge rate, the one that had been noticeably slower than the young groups before supplementation, came back completely in line with it afterward. The gap didn't just shrink. In this specific measurement, it closed. There was a smaller, less dramatic finding buried in the same study worth mentioning, honestly. Across both groups combined, people were also able to keep exercising longer before reaching exhaustion after taking creatine. A real, useful buffer, even if it wasn't the kind of age-specific, doubled effect the phosphocreatine numbers showed. That's the study behind the number I promised you at the start of this video, and now you actually have the mechanism to understand why it happened, instead of just hearing it as a surprising statistic. It isn't magic, and it isn't that creatine works differently in older muscle. It's the exact same molecule doing the exact same job in both groups. The difference is where each group started. A tank that's already 3/4 full doesn't have much room left to fill. A tank that's been running low for years has a lot of room. And when you finally top it off, the percentage change looks dramatically larger, even though the underlying process is identical. This single study from 1998 isn't the whole picture on its own, of course. Since then, a much larger body of research, including extensive work out of the University of Regina's Aging Muscle and Bone Health Laboratory under researcher Darren Kandow, has tracked similar patterns across older adults well into their 60s, 70s, and beyond, consistently finding that creatine paired with resistance training moves the needle on lean muscle mass and strength more than resistance. Training does on its own in this population. Now, refilling the battery faster is one real, useful thing. But if that were the whole story, this would be a fairly narrow, technical video about exercise performance in a lab. There's a second effect, operating on an entirely different piece of the aging puzzle, and it's arguably the more important one for anyone thinking about long-term independence rather than leg press numbers. Building new muscle, or even just repairing and maintaining what you already have, isn't something a muscle fiber does entirely on its own. Muscle relies on a population of dedicated repair cells sitting on the outside of each fiber, called satellite cells, which activate after strain or damage, multiply, and in some cases fuse directly into the fiber itself, donating their nucleus to help run the expanded machinery of a larger, stronger cell. Here's a detail worth sitting with. Most cells in your body carry a single nucleus, but muscle fibers carry many, strung out along their length, because a single nucleus can only oversee a limited stretch of surrounding cell material. Researchers sometimes call that its domain. A bigger, stronger fiber genuinely needs more nuclei running it, the same way a bigger factory floor needs more than one supervisor on it. Fewer available nuclei per fiber generally means a slower, more limited capacity to grow or repair. And here's the aging-specific problem. Research measuring satellite cell populations directly in human muscle biopsies has consistently found fewer of these repair cells in older adults than in younger ones, with the shortage landing hardest, once again, in type I fibers. The very same fibers already running short on battery capacity. This same shortage also helps explain something clinicians have long noticed. When older muscle is injured, or simply goes unused for a stretch, a hospital stay, an illness, even a couple of weeks in a cast, it tends to come back more slowly, and sometimes less completely, than younger muscle recovering from the identical setback. The repair crew itself is smaller, so the rebuild takes longer. This is where a study out of Copenhagen becomes relevant. In 2006, researchers led by Michael Kjær published results from a 16-week strength training program comparing men who took creatine against men who took a placebo. Every group that trained gained some new satellite cells and myonuclei, which makes sense. Training itself stimulates repair. But the men taking creatine showed a significantly larger jump in both measurements than the men on placebo did on the identical training program. Worth being precise here. That particular study was done in men in their 20s, not older adults, so I won't pretend it proves the effect is bigger in aging muscle specifically. What it proves is that the mechanism itself is real. Creatine measurably amplifies the muscle's own repair cell response to training. And once you already know that older muscle starts with a smaller pool of these repair cells to begin with, the same more room to fill logic from the battery story applies again, just one biological layer deeper. A lever that helps even a fully stocked young system is a reasonable bet to help more in a system running short on the very resource that lever pulls. There's a plausible reason this happens at the cellular level, too, and it connects to something you may have heard about creatine and dismissed as a minor side note. It draws water into the muscle cell. That's not a cosmetic effect. A cell that swells slightly with fluid appears to register, through its own internal signaling, as a cue related to growth. The same general category of signal your body uses to help decide whether conditions favor building tissue or breaking it down. Researchers studying why older muscle responds sluggishly to the normal building signals. A phenomenon in the science called anabolic resistance, studied extensively by groups including Stuart Phillips's lab at McMaster University, have pointed to exactly this kind of blunted signaling as part of the problem. Creatine's cell swelling effect won't reverse anabolic resistance on its own, and nobody's serious claims it does. But it's a small, additional nudge toward the build side of that signaling balance on top of a training stimulus. And small nudges tend to matter more when the starting signal is already weak. So we've gone from a half-second wobble at the edge of a table, down into a specific fiber type, down into a specific molecule inside that fiber, down into why that molecule runs low with age, down into a study that measured a 5-day supplementation protocol closing that gap inside an MRI machine, and now down into the actual repair cell population responsible for whether that improvement holds up, over months rather than fading after one good week. Each layer explains the one above it. None of these are separate stories bolted together. They're the same story, getting more specific. Why does any of this matter beyond a number on a lab printout? Because the fibers we've been discussing this whole time, the fast, explosive, phosphocreatine-rich, satellite cell-hungry ones, are exactly the fibers responsible for a very specific, very consequential category of movement: the catch, the stumble recovery, the quick shift of weight that keeps a trip from becoming a fall. Darren Kandau's research group, the same lab behind much of the strength and lean mass data I mentioned earlier, has specifically studied creatine's relationship to fall and fracture risk in older adults, alongside bone density outcomes in postmenopausal women. I want to be honest about the strength of that particular connection. This is a logical, mechanistically grounded relationship, not a claim that creatine has been proven in a large trial to directly cut a specific number of falls. But the biological thread is straightforward and worth taking seriously. The exact tissue this molecule appears to support most is the exact tissue your body deploys in the split second between a stumble and a fall. In practice, that broader research record shows up as measurable improvements in the kinds of tasks that mirror real-world independence directly. How many times someone can rise from a chair without using their hands in 30 seconds, how fast they can cover a short walking distance, how much force their grip can produce. So what do you actually do with all of this? First, pair it with resistance training, and don't skip that part, expecting the supplement to do the work alone. Everything we just covered about satellite cells and repair signaling only switches on in response to a training stimulus. Creatine amplifies a building response that has to already be underway. 2 or 3 sessions a week, working the major muscle groups against real resistance, is what gives the molecule something to amplify. There's even research narrowing down when, specifically, to take it. A 32-week study following adults in their 50s, 60s, and early 70s found that taking creatine immediately after a workout, rather than before it, produced meaningfully larger gains in lean tissue mass. Which fits the mechanism neatly, since the muscle's own uptake and repair machinery is at its most active right after you've just finished, asking it to work. Second, think in terms of weeks, not doses. The entire mechanism we've walked through is about gradually raising a chronically low reservoir, not flipping a switch. A steady daily amount, commonly somewhere around 3 to 5 grams, sustained over time, is what the research protocols showing benefit in older adults typically used. Worth knowing. The Boston University study I described earlier actually used something close to a short loading protocol, a higher amount for just 5 days, which is one legitimate way to get there faster. The research in older adults has tested both that approach and simply starting at a lower daily amount and letting levels rise gradually over 3 or 4 weeks. Both routes appear to arrive at roughly the same place. The loading phase just shortens the trip. It isn't a requirement. And if your own diet leans light on meat and fish, remember the primary dietary sources of creatine. You may be starting from an even lower baseline than most people, which, based on everything we covered about tanks with more room to fill, would predict an even larger relative response to supplementing. Third, keep your water intake steady as you build this into a routine. Remember that the mechanism draws fluid into the muscle cell itself. That's a feature of how it works, not a warning sign. If you notice a small uptick on the bathroom scale in the first couple of weeks, that's very likely this exact process, water moving into muscle tissue, not fat gained or anything to be concerned about. And fourth, this one is simple good sense rather than anything specific to today's topic. If you manage a kidney condition, take regular medication, or are just unsure how a new supplement fits your particular health picture, have that conversation with your doctor before starting. Large reviews pooling data across many studies and thousands of participants, including structured analyses looking specifically at whether higher doses or longer duration raise the rate of side effects, have consistently failed to find evidence of harm to kidney function in people who started out with healthy kidneys. It also happens to be one of the most heavily studied supplements in existence, with sports nutrition bodies tracking its safety literature for decades now, which is part of why the research in older populations specifically has had room to grow as large as it has. Still, that's reassuring information about populations, not about your particular chart, and a 5-minute conversation costs you nothing. Think back to that half second at the edge of the table, the one we started with. I don't want you to hear it anymore as a small failure of your body, some vague sign of things generally winding down. It isn't general, it's remarkably specific. One type of fiber, one type of energy reserve, one repair cell population, all quietly running leaner than they used to. Aging, it turns out, is not one thing happening everywhere in you at once. It's thousands of small, mostly separate stories, each with its own timeline, its own cause, and, as this one happens to show, sometimes its own remedy. And that specificity is actually the hopeful part of this whole story, because specific, well-mapped mechanisms are exactly the kind biology tends to let us influence. You didn't lose your balance because you got old in some vague, unstoppable way. You lost a little of one particular battery in one particular fiber that happens to have a remarkably well-studied way of being partially refilled. Whatever you decide to do with that information is yours to decide. But I'd rather you carry the accurate story than the vague one, because the vague story only ever tells you to accept the wobble, and the accurate one tells you exactly where to go looking, if you'd rather not.